Here we're looking at exponential functions and exponential modeling, something that is in the news a lot at the moment because the reason we're doing this via video is that there is a quarantine on because of the fact that viruses grow exponentially. You'll have heard a lot about exponential models in the news probably recently. We're not going to discuss anything to do with that in this video, rather the underlying maths of how exponential functions work and what they can be used to model in addition to global pandemics. So an exponential function is just a function that has the variable input in the exponent position. In other words, the variable is the power. So this is an exponential function here, y equals 4 to the power of x plus 1. Because the input variable, the x, is in the power position, the exponent position, that makes it an exponential function. You do not have an exponential function if you have something like this, y equals x to the power of 4. That is not exponential because the power is constant and it's this thing here that changes. So that's not exponential, whereas the one in blue is. So they have a couple of characteristics which you need to be aware of. And in the notes for this lesson, which is this big page here, this just goes through all the different types of things you will see in an exponential function. We need to read through that, but I'm just going to try and explain some of those in more simple terms for you with some diagrams. So this is an exponential function here, y equals 4 to the power of x plus 1. One thing you will see with exponential functions always is that there is a change in growth rate. So here is quite slow, but then as the values of x increase, you get a change in growth rate. It gets more rapid. That can happen the other way around. It can start slowing down the other way as well, depending on what the values are. But a change in growth rate. So you haven't got a linear path going from one side to the other. It's a changing gradient growth rate there. You've always got a horizontal asymptote. So that's a value above or below which the function will never go beyond. So in this case, you can see that if we carry on going down here, the function is going to level off and it's never going to go below the line y equals 1. Now you can see that from the original function here. Let's just have a think about why that would be. So actually I'll put this line on here as well. So it's going to be roughly there. That's that line there. The reason that's the case is that if we go to the function here, if we make this x value really, really big, 4 to the power of 1,000,000, that's going to be some huge value. So that's going to go off into infinity. If you start making the x very, very small, let's say you have some negative numbers, negative 10, negative 20, negative 1,000,000, negative powers don't produce negative numbers. In fact, they produce fractions. So if I just gave you an example of a negative power, let's say it was minus 2. What happens there is it's the same as 1 over 4 squared, so 1 over 16. Now that's a very small number and it's going to get smaller and smaller and smaller as the negative value increases, but it's never going to reach 0. That means the function overall, this is going to get to 0. It's effectively going to be 0 plus 1. So that's where you get this y equals 1 asymptote from. They've also got a y-intercept value, and in this case the y-intercept is when x equals 0, and that's always the case with any function actually. If you make the x equals 0 in this function here, well, anything to the power of 0 is 1, so that means that's going to become 1 plus 1, so the y-intercept value there is 2. Because that thing becomes a 1 there. So those are the features of a basic exponential function. We'll have a look at a few variations of that. So the first important one is this. Now this is actually a mirror image of the one we were just looking at. What's changed here is that instead of it being 4 to the power of x, it's 0.25 to the power of x. I've chosen that one deliberately because of course that is the reciprocal of 4. That's a quarter as a decimal. So that means that if you increase the power here, you are multiplying repeatedly by a quarter rather than by 4. So you can see what happens as that x gets bigger, the value of the function gets smaller and smaller and smaller. However, you can make the x as big as you want, it's never going to go below 0. So this actually has the same horizontal asymptote as before. So you've got that y equals 1 horizontal asymptote that is never going to go below. because that thing there is never going to get lower than 0. As you get negative values, you're going to have things like, let's put the -2 in again. Well, if we do 0.25 to the power of -2, remember that's a fraction, it's going to be 1 over 0.25 squared. Well, 0.25 squared is going to be some small decimal, or 0.0625. 1 over that, though, is going to be a big number. Dividing by that decimal there makes it bigger and bigger and bigger. So it goes off into infinity, into the negatives. That's a general rule here. If you've got a value of a, where a is this number here, that is between -1 and 1, like it is in this case, then you get a decreasing function. And it'll be increasing if a has a magnitude that is greater than 1 or less than -1. So this is also exponential. It's not the exponential ones you'll be hearing about with the virus, but it is also an exponential curve, and it's used quite a lot in other situations. One other thing to note as well is that you can have a constant number, multiplying the exponent number here. So this is the same function as before, except I've just multiplied the 4 to the power of x by 2, and that doesn't change everything about it. You still get the same horizontal asymptote situation, because again, if this power of x gets really, really negative, this whole thing here is going to get close to 0. Well, 2 times 0 is still 0, so you're still going to have that horizontal asymptote there of y equals 1, because that whole thing is going to become 0. What does change, though, is the y-intercept. So in this case, if the x is 0 here, then what happens is you get 2 times 4 to the power of 0 plus 1. Well, that is not 0, it's 1. Therefore, you're going to get 2 times 1 plus 1. So 2 times 1 is 2, plus 1 is 3. So in this case, we'd have a y-intercept of 3. So it becomes essentially whatever number is here plus any constant there, because that's become a 1. One more thing to look at with exponential functions is right at the bottom of the notes page there. You'll see, I think, quite a confusing set of algebraic terms, but let me see if I can explain where those have come from. So if you get something that looks like this is also an exponential function, but it's more complicated because we've got the 2 as before, we've got the plus 1 here, but the power of the 4 isn't just x, it's actually 3x plus 7, and that's something you can have. This power can be a more complicated function of x in itself, but you can break these down. So if you remember from indices laws, if you have same bases and you're multiplying them, you're going to add the powers. So if we have 4 to the x multiplied by 4 to the 7, that could be written like this, because you add the powers when you multiply. So in a minute, I'm going to do the reverse of this process. I'm going to break this down. We've got powers here being added, so I'm going to break that down into 2 bases being multiplied. Another thing going on here as well is if you have a 4 to the 3 bracket all to the power of x, you would multiply those two, it would give you that. Again, I'm going to do the reverse process in a second, because you can see you've got 4 to the power of 3x here. Well, I could break that down into this. So remember these 2 steps here, and see if I can apply them to this function here. So keep the y on that side. Okay, so 2 there, and this 4 can be written as follows. I'm going to take the 4 to the 7, and I'm going to multiply it by this here. So I've done this with the 2 steps I showed before. 4 to the 7 multiplied by, and it's multiplied because when you're adding the powers, that means you're going to be multiplying the original base numbers with those individual powers. And then the 3x I've written like this. The reason for doing that is that, well, now the front I've got 2 times 4 to the 7. That is just a number. I'm not actually sure what that is. Let me just go on the calculator and work it out, but I'm just going to do 2 multiplied by 4 to the power of 7, and it's 32768, so that's what goes there. And 4 to the 3, I know that one is 64 actually, so I'm going to just put in 64, I'm going to write that in there, to the power of x, and then there's +1 at the end. So that is a more simple way of writing this function. I've managed to take some of the values out of the power here, and using indices laws in reverse, I've managed to simplify it to this. This is a bit more simple because it is just a constant number and a single constant here, and now a single x in the power. You'd rather have this than this. So that comes up a few times. Look out for that in some of the example questions. We'll look at the examples in the notes now. These aren't too complicated, I don't think, so a lot of them I'm going to leave you to look at yourself. This first one especially, a lot of that just covers what I was just looking at, so read through that, see if you can see where the answers come from. If you're unsure about anything, put these functions into Desmos. I'd use that rather than the GDC graphing calculator, so put them into Desmos and see if you can see the connection between the functions and some of the questions that are being asked about it there. In this modelling question here, this is a fairly straightforward use of the functions. I'm going to point out a couple of things here. So a lot of exponential questions work in terms of time, and you'll be given some information about the situation at the beginning of time. So in this case, it's some radioactive material, and it wants to determine the original mass of that. Original means when time is 0. So you're just going to change the power, which is the time, to 0. Of course, that's going to turn this whole thing here into 1, so your answer is just going to be that there. So time is 0 in that initial question. The mass after 1 decade, don't be confused with the nth term where you have n minus 1 as the power. In this case, it's after 1 decade, so we need to apply this multiplication process 10 times, so the power does need to be 10. In the next question, we have to use the equation solver to work out this here. Again, I'm going to let you figure that one out yourself, but use the equation solver for part C and part D in that. Just think about what the unknown, the x, has to be in this question as you put it into the equation solver. Question 13, I'm going to show something from question 13 because there's a very common step in this question you're going to need in a lot of other questions. So this is one about an investment fund, the value of the fund, and it's given by the function v of t equals v0 e to the power of kt. Now e is going to come up a lot later. We did see it earlier in the year, Euler's number. We're not going to dwell on it right now, but it happens to be used a lot in exponential functions, which you'll see in a minute. So in this question, we're trying to work out what the v0 actually is, this constant in front here. We are told that the initial amount in the account is 5,000 euros. Well, it's saying the initial amount, so that means that time is 0. So we put 5,000 there in the value. We don't know what this constant here is going to be just yet, but we don't know what k is either actually, but we do know that time is 0. Well, if that's 0, it doesn't matter what k is, that whole thing's going to be 0. Anything to the power of 0 is 1, so you get this. The v0 is just 5,000 in that case. On the next question, you again, you're going to use the GDC equation solver to figure that out. Just make sure you correctly work out an increase of 25% on the original amount. Stick that into the output or the answer value. You've got the V0. The unknown part in this question is the K, because we're told that time is 6, because it's after 6 years. And hopefully you'll get the answer that's in the question there. Very last example is a modelling question. I think you'll find this one fairly straightforward. It follows a very similar pattern to the modelling problems with other functions. So stick the data into the GDC. A couple of things to note when you do that is make sure you're putting the data into the right lists. Conventionally, you're going to put the x-axis into list 1 and the y-axis list 2. The x-axis is the weeks. It's just going to be 1, 2, 3, 4, 5, 6 up to 20. The views in this particular question is the y-axis, so put that into list 2. When you're doing the regression, you're going to go to calculation, you're going to go to regression as usual. you're not going to be picking any of these, linear, quadratic, cubic. You're going to go across to the exp, that's the exponential. I mentioned earlier that e is a very common number in exponential questions, and you can see it here again. We're not using that in this question though, that's going to come up later, so you don't want to pick that. Pick the second function here, that's just standard ab to the power of x. You can press F2 there, and if you put everything in right, it should give you the same values as in the example. So do work through those examples, do send in any questions you have, you're not sure, and then try the exercises afterwards.